All right, so the last time we met, we were finishing up page 13, and I had you work on these problems outside of class. So I'm going to put the answers up here. So number 3, how many grams are in 125 milligrams? So 125 milligrams over 1. In 1 gram, there are 1,000 milligrams. So you're dividing by 1,000. That's the same as moving a decimal to the left 3 places. So you end up with 0.125 grams. Questions on that one? All right, number 4. The sleeve of a shirt is 20 inches long. How many millimeters is this shirt sleeve? So our starting quantity is 20.0 inches. It's very easy not to copy down that 0.0 and just copy down 20. And then you would only have 1 sig fig, so watch out for that. So now I'm going to convert inches to centimeters, centimeters to millimeters. So 1 inch, 2.54 centimeters, and then 1 centimeter is 10 millimeters. My units cancel out, and I end up in millimeters. How many significant figures should I have in my answer? 3. So I end up with 508 millimeters. Any questions on that one? And on page 14, number 6. So this question, it might have taken a little bit of work to get it set up because you're thinking, density, how do I use this? Your starting quantity is here. So you're starting off in grams, and the question is looking for cubic centimeters. So you have a conversion factor right here that goes from grams to cubic centimeters. So you can have 2.70 grams over 1 cubic centimeter, or 1 cubic centimeter over 2.70 grams. So my starting quantity is 200.0 grams over 1. Again, this is another problem where if you don't copy down all of the zeros, you can get thrown off with your significant figures. So in order to get grams to cancel out, which way am I going to have to use this conversion factor? Second one. So 2.70 grams over 1 cubic centimeter. Grams cancels out. So 200 divided by 2.7 gives you 74.074. And that's cubic centimeters. Now, sig figs on this one. So far, sorry about that. So far, you would think your starting quantity has 4 sig figs. Right? So 4 sig figs here. My answer should have 4 sig figs. We are going to learn about density. And you measure density in lab. And remember that you had to measure what 2 quantities in density? Mass and volume. So density is a measured quantity as well. So it's not an exact number. It's a measured number, and we'll go over this more. So this is measured. And because it's measured, you have to pay attention to sig figs. So now, if you have a conversion factor that involves density, you have to look at the significant figures there too. So this is 3 sig figs. And then you treat it like you would with the multiplication and division rules. So I have 4 sig figs and I have 3 sig figs. What's the rule with multiplication and division? The smaller. So I can only have 3 sig figs in my answer. So how would I adjust this to 3 sig figs? After the 0, good. So then my answer comes out to be 74.1 cubic centimeters. And if that went over your head right now, that's okay. You're thinking, oh, I was sure it was 4 sig figs. That's okay. We're going to go over it more coming up. So just, you know, as long as you think about it, density is a measured quantity. Questions on that one? Number 7. Number 7 is like that pink book problem that I went over the other night. Remember, when you have something squared, it's something times each other twice, right? So this is really 0.25 centimeters times centimeters over 1. What conversion factor am I going to use?
1 centimeter.
Okay, so 1 centimeter on the bottom, and then how many micrometers? 10,000. And you do that twice. Very good. So 1 centimeter cancels out here. If we stopped right here, it would be centimeters, micrometers. But we got to keep going because the question asks for it in micrometers squared. So we're going to do this again, like I heard a lot of you saying. So then 0.25 times 10,000 times 10,000. So you should have 6 zeros, 25 million. Micrometers squared. If putting that many zeros is making you uncomfortable, you can always express it in scientific notation. The way you would do that, 2.5 times 10 to the 7th micrometers squared. Do I have the correct number of sig figs?
Yes. Yep.
Yes. So as long as you don't put a decimal point on your 25 million, you know that's where you might make a mistake. But yes, that does have the correct number of significant figures. 2. Very good. Any questions on that one? Alrighty, number 8. So we're trying to get kilometers. Let me start over again. Miles per hour. We want to get that to kilometers per hour. Do I need to do any converting with the time? No, you're there. But I need to convert miles to kilometers. How do I go about that?
Miles to feet.
Miles to feet, yes.
Inches.
Feet to inches. Inches to centimeters. Did anybody do it differently?
Yeah, make it meters.
Inches to meters.
Meters.
But you know that, so if you know you make it complicated, that's a good thing.
Come out with the same answer. So.
Yes, you will. That's right. Okay, so we will have 85. And how are we going to write out this starting quantity?
85 miles an hour.
85 miles over 1 hour. Okay. And then what do I do next?
You wanna put miles on it?
So, okay, so 1 mile, and then 5,280 feet. Miles cancel. And then feet to inches, and 1 foot, how many inches are there? 12 inches. Inches to meters. So 39.4 inches in 1 meter. And then meters to kilometers, so 1 kilometer is equal to 1,000 meters. So meters cancel. Be careful on conversion factors like that one. It is very easy to flip things around. I find students a lot of times saying, well, in 1 meter, there are 1,000 kilometers. Things like that. So just step back for a second when you're at this place on a quiz or an exam and say to yourself, is a kilometer bigger or smaller than a meter? Does this make sense? So with this conversion factor, I would say, oh, okay, a kilometer is larger than a meter, so it's going to take more meters to make up a kilometer. Okay? It's just,
You could also do it to, could you do it to where it was like 1 meter and then 0.001 kilometer?
yes.
Okay.
And then ask yourself the same question too with that one.
Okay.
All right, so in my calculator, well, how would I enter this into my calculator? This is another tricky point. Sometimes you do all the work and then you enter it incorrectly into your calculator.
You can multiply the top and you divide with the bottom two.
Right, so you can multiply everything on the top, make sure you get everything. You read everything left to right. So 85 times 5,280 times 12 divided by 39.4 divided by 1,000. So I ended up with 136.69 kilometers per hour. How do I adjust for sig figs? How many sig figs should I have? 2. So I will have my bracket here. What will that round to? 140 kilometers per hour. Yes?
So would you count off if I just did miles to kilometers? Would you want us to show?
If you did miles to kilometers, if you found your own conversion factor, that's fine. Especially on something where you're taking it home.
Okay.
But you might find it hard on a quiz or an exam to, unless you had it memorized, which I do have students who have conversion factors memorized. So, if that came up, for sure. Did you end up with the same answer?
Yeah.
Good. Yes, yeah, another question.
Are you going to give us like the conversion factors for like just like or like feet to miles and stuff? Will you give those on the test?
Yes.
Okay.
Yes, you don't have to memorize those. Other questions? No? Okay. So conversions, I was telling some students earlier, conversions are definitely the hardest part of Unit 1. So if you find them to be challenging, that is what I would expect. I always expect conversions to be challenging. By far the most difficult thing, again, in Unit 1 is conversions. So if you need to go back and review conversions, it will be worth it. The exam has a lot of conversion problems. The other reason it will be worth it is because coming up, Unit 2 will see more conversions. Unit 5 will see a lot of conversions. Chemistry is a science of conversions. So we're not going to forget about conversions. We're going to keep them going. So if you master them now, the rest of your work throughout the semester will be a lot easier. So if you're still struggling with these after practicing a lot, work on it some more. You have a long weekend, take some time, get some help. It's definitely worth it. Questions? All right, so now we're going to move on to density. So we have had a density lab, and so at first you might be thinking, I haven't even learned this yet, but we had a density lab. And so sometimes when we have lab before a lecture, it can actually be more memorable because it's so shocking when you see it in lab that, oh yes, I remember doing this. So let's move on. So density relates mass to volume. Density is defined as mass over volume. The units that you typically see for density, if it's a liquid, you see units of grams per milliliter. And keep in mind, when you're working with any unit that has two units, one in the numerator, one in the denominator, you can see it written out several ways. You can see it written with a slash, like this. Or you can even see it written in a crazier way. And I'll show you this too. But you're going to be well prepared. You know what to expect. Grams, milliliters to the -1. So for a liquid, you can see liquid, it's either grams per milliliter, written like that, grams / milliliters, or grams times inverse milliliters, which is the same thing. But it looks really confusing when you see it like that. Anytime you're given density, I highly recommend writing the units out like this, just like what we were doing with velocity, right? The miles per hour, kilometers per hour. Write it over the numerator over the denominator. The other unit that you can see for density is for solid, grams per cubic centimeter, and I'll write it all the crazy ways.
This is maybe kind of jumping ahead with it, but I did the quiz, like the online practice quiz that they have,
Okay, so you did the online quiz.
and like the last two of them, when it got to, it started instead of saying density, it was using this
Specific gravity.
and then so it kind of like made me go blank for a second, and then I looked at the 2 pages you had us do, and it talked about how there's no units, so you don't really have to worry about units. You just kind of plug it in as if it was density.
Yeah, you are totally on the right track. We will talk about specific gravity, and it is pretty much density without units. So then you just put the units on and solve it. But good that you're working ahead. I have listed the densities of several different items, and you're familiar with these things. And you know a lot about density already, believe it or not. Just what you use intuitively. You know that there are certain things that float in water. There are certain things that sink in water. That is related to density. So ice, it floats in water because ice is less dense than water. Now, if you prepare an alcoholic beverage, and you put ice in it with just alcohol, neat alcohol, the ice will sink. because if you look at the density of alcohol is lower than that of ice. So the ice will go to the bottom. So if anybody ever says, I have an experiment for you. I want you to see if you can tell which substance is water and which substance is alcohol. You know, they're both clear. They both have ice in them. The one where the ice floats, water. The one where the ice sinks is alcohol. Yes, I'm thinking. Now, there's also the other big giveaway, which is the smell, right? You could smell it or the taste, but so I went to a hot tub store one time with one of my friends, and she was very interested in getting a hot tub, and so, you know, the salesman was going about his spiel because he wanted to make that sale, because they're pretty expensive, you know, it's a big deal, but so he had, you know, all these different models that he was showing us, and then he said something like, well, you know, women are more buoyant than men. And so I was thinking, so what he's saying is that women have a higher body fat percentage than men, right? So you're more likely to float. So that's what he was getting at. Because the way this hot tub was oriented, it was better for women. So that's, you know, but so now you know, if you look at body fat is less dense than water. So it makes sense that you would be more buoyant. I always tell the story when I go over density. One time, my husband and I went to a gas station. This was before we had kids, long ago. And so we needed to get gas. We got gas, and it was an automatic transmission, relatively new car. I'd been running fine, no problems whatsoever. After we got the gas, turned over the ignition, and it wouldn't. It started, and then it stalled out. They'd never done that before. Never had any problems like that. Tried to start it again. The same thing happened. And so, fortunately, we weren't that far away from where we lived at the time, so we just pushed the car into a parking place. The next day, had AAA come, and AAA tried to jump it, nothing, no success whatsoever. So they towed it to the dealership. And then I was, at the time, I was teaching and working in industry. And so I was working my day job, and the dealership calls me and they say, yeah, you don't put water in your gas tank. Oh, thanks. I'm pretty aware that you don't put water in your gas tank, but, you know, it was not sold as water. So then I end up calling the gas station, and the gas station says, oh, there's no way we could have any water in our gas tanks. We have these special filters, and they shut the gas off if there's any water that comes through, if it detects. Well, it didn't. So, you know, then I got to thinking, how can I prove this? Because they weren't going to pay for this at this point. And so it was however much gasoline was at the time, and then it was about $400 to get all the lines cleaned out so that it would work again. So I was talking to some of my coworkers because I was, you know, working a chemistry job, and I said, well, you should just, you know, get a sample, and, you know, then we can analyze it, because we had all this fancy equipment. And I'm like, oh yeah, that's what I'm going to do. I'm really going to stick it to them. And I didn't think at the time, you know, well, what do I know about gasoline? What do I know about water? Think about the density of gasoline and water. So we really don't have to run any experiments on it. You can just get a sample of it. So then I called the dealership, and, you know, they just thought I was so stupid for putting water in my gas tank. Like, hey, would you mind saving a sample of this? You know, so sure, we can do that for you. So they gave me a sample, and it was like a blue bottled water, you know. So I look at it when we go pick up the car, and it is this brown, muddy water on the bottom. And then at the very top, there is a fine, thin, like golden bit of gasoline. So very evident that there was water in the gas tanks where they stored their gasoline. So We went to the gas station. They said, well, yeah, it turns out we've had a few other calls that, and because there was less water that went through, it actually did far more damage than just $400. It was getting into the thousands of dollars. So at this point, they agreed to reimburse me. They recognized that they had been at fault. And with this particular gas station, it was in the middle of a hill, which you don't find many hills in Kansas, right? But it was in the middle of a hill. And when it would rain a lot, somehow water would get into their gas tanks. So we never went to that gas station again. But I learned a good lesson, like thinking I needed all these sophisticated tests to prove that there was water in this gasoline, when all it was I just needed the sample. So since gasoline is less dense than water. So that's my density example. But, all right. So the gasoline probably has a density of about 0.1 or 0.81 grams per milliliter. So it definitely would float on this water. So back to page 15. When you're measuring out liquids, if you think about the balance that we've used in lab, and you think, well, I can't really pour a liquid onto the balance to figure out the mass. It's very useful to use density instead. So then you can just measure the volume. So if you want to measure out 1.5 grams of ethanol, but you don't have a scale, you can use a graduated cylinder instead, which measures volume. So how many milliliters of ethanol are there in 1.50 grams? You would have to be given the density in order to solve this problem. So you're going to use that density. And again, it's a measured number. So just like our conversion problems that we finished working on, you would set it up the same way. 1.50 grams over 1. And since you're so well prepared, you know that grams / milliliters means that. So in order to get the grams to cancel out in this problem, what do I have to do? Flip it. Excellent. So grams cancels. You're in milliliters. So I would do 1.5 divided by 0.789. How many significant figures would I use? 1.9014. So I have 3 sig figs here. And now I have to look at my density. 3 sig figs here. So you're right. 3 sig figs. What are my units? Milliliters. So if you didn't have a balance, you could use a graduated cylinder and measure out 1.90 milliliters.